invoke Lord's gracious presence in this opportune moment.
Thank you. Let us pray. Our most loving Heavenly Father, with thy children come to the throne of grace this evening, O Lord. Lord, we praise you and thank you for the hope, joy, and love we have in you, O Lord. Thank you, Lord, all the privileges we have in you. Thank you in our life. We feel the security, care, and protections these days, especially amidst of the pandemic disturbances, O Lord. At this time, we thank you for all the opportunities we have as faculty members, especially a student friend joined here in a very good learning environment through online, O Lord. Thank you, Lord, for the wonderful program, the 3 days online workshop on X-ray diffraction, organized by the American College Central Instrumentation Center. Lord, we thank you and praise you for our principal and secretary, Dr. Daumani Christopher, for his encouragements, support in establishing this kind of facilities, infrastructure facilities, up to the level of further research of our students in our campus itself, oh Lord. Thank you for the wonderful infrastructure and all his support. Bless him, bless all his works have done, oh Lord. Lord, we thank you for Dr. Jemima Balaselvi and her team, for organizing this wonderful program through this center, oh Lord. Bless them all and prosper all their plans. At this time also, we praise and thank you, Lord, for the presence of Dr. Swarna Durai from IG Core Kalpakam. Thank you, Lord, for his acceptance and the presence online, for sharing his expertise among our students for these 2 days, O Lord. Bless him, bless all his responsibilities, bless all his preparations, he plans, which he wants to share among our students for the research work and the studies, O Lord. Give us all a good time of learning, progress in their education of our students. We commit each of our participants in your mighty presence. Be with us, O Lord, lead us and guide us. Let it be a wonderful, beneficial, and fruitful days of our students and faculty friends through this wonderful program. Prayer in the mighty name of our Lord and Savior Jesus Christ. Amen.
I invite Dr. S. Israel Convener, Assistant Professor of Physics, Additional Dean for Curriculum Development and Research, to welcome our guests and participants.
Good evening, everybody. It is my pleasure and it's my privilege to be here on this particular occasion on the inauguration session of the 3 days online workshop on X-ray diffraction conducted by the American College Central Instrumentation Center. And I'm really thankful to Dr. Jemima for giving me the opportunity to give a welcome address here. I welcome every single one of you who are all present here for this particular occasion. Especially I welcome Dr. M. Daumani Christopher, Principal and Secretary of this college, and I welcome Dr. Sheila, the Bursar of the institution, and other ex officio members who are all present here for this particular occasion. And I'm welcoming Dr. D. Swarna Durai, the special invitee who will be delivering lectures for 2 days on the introduction to X-ray powder diffraction and the guidance to powder X-ray diffraction and data analysis. I welcome you, sir, Dr. D. Swarna Durai, Scientific Officer from IG Kalpakam. I welcome you all. I welcome you to this particular occasion and to our college, and we are really privileged to have you here as a special guest and as the chief invitee. And I welcome every single person who are all present here. I welcome all the deans, additional deans, and other members of the faculty from American College and from other colleges. I welcome all the students from our college and from other colleges. I welcome one and all for the wonderful occasion where we will be learning things. It's not only hearing, but actually it's a learning process where in the workshop actually you will learn many different things that will be put in use for your own future work and for your own research work and so on. I welcome you all and I thank this opportunity. I thank Dr. Jemima for giving me this opportunity to welcome each and everybody who are all present here. Thank you very much.
My privilege to invite our Principal and Secretary, Dr. M. Daumani Christopher, to address the gathering with his inaugural speech.
Good evening, friends. Hope you can hear my voice.
Yes, sir. Yes, sir.
Thank you, sir. 3 days online workshop on X-ray diffraction. It's not that I'm so smart. It's just that I stay with problems longer by Albert Einstein. Congratulations to the director of ACCIC, American College Central Instrumentation Center, Dr. S. Jemima Balaselvi Juliana, who is also the program coordinator of the webinar. Dr. Israel, Associate Professor of Physics and convener of the webinar, and co-convener Dr. E. Johnson Christudas, Assistant Professor of Microbiology. To the resource persons, Dr. Sornadurai, the Scientific Officer, X-ray Scattering and Crystal Growth Section, IGCAR Kalpakam, and Dr. Israel, the Additional Dean of Research, the American College, for accepting our request to be the resource persons. ACCIC is a recently established department headed by Dr. Jemima, a very good researcher and associate professor from the Department of Chemistry of our college. Very recently, American College Central Instrumentation Center was organized series of webinars. Now they are doing their 3-day webinar. Friends, we are in a corona pandemic period. WHO announced that COVID-19 can be characterized as a pandemic in 13th March 2020. Almost 16 months have gone. Entire world kept quiet even after 16 months. Now, no one knows what to do. But we have to find out how to overcome these kind of hurdles and problems that the entire humanity expecting now. Anything we have to take it in positive sense. We have to adapt ourselves for any situation. It's a God-given break. God gave a chance to think about our future. Yes, it's a God-given break in the fast and furious and chemical world. It is an exercise to all to face tomorrow's world. Let us all face boldly. In this kind of situation, ACCIC is voluntarily came forward to conduct a 3-day online workshop on X-ray diffraction to their students, staff, researchers, and of course public. As I said earlier, it is not that I am so smart. It's just that I stay with problems longer. God gave a chance to apply our mind to imagine now. I do appreciate their interest in organizing such a useful webinar. I am happy to inform you that the American College is the only college having this kind of facility, that is ACCIC, to serve the researchers and works in and around Madurai Kamaraj University zone. Friends, I am happy to inaugurate this 3-day webinar on X-ray diffraction organized by the ACCIC to their students, researchers, and public during the lockdown period caused by coronavirus pandemic. ACCIC has planned to have 3 different sessions. The first session will be conducted by Dr. Sornadurai on Introduction to X-ray powder diffraction. Second session also by Dr. Sornadurai, the scientific officer from IGCA, on the same topic, guidance to powder X-ray diffraction data analysis. And the third session will be on softwares and tools for XRD analysis by Dr. Israel, the Additional Dean of Research, the American College. It's my pleasure to thank again the resource persons for accepting our request. Hope it will be useful to all. Once again, I congratulate the Director of ACCIC, Dr. Jemima Balaselvi, Convener Dr. Israel, Co-Convener Dr. Johnson Christadas, and Executive Members Mrs. Jennifer Michelin Kiruba of Microbiology Department and Dr. Jansinani of Chemistry Department for their wonderful initiative. God bless.
Thank you, sir. Thank you for your gracious words. Now I request our principal to release the proceedings of the workshop. We present you the proceedings of the 3-day online workshop on X-ray diffraction, which contains modules of different technical sessions handled
Happy to release the proceedings of the 3-day online workshop on X-ray diffraction, 30 and 31st of July and 2nd August, organized by the American College Central Instrumentation Center. God bless.
Thank you, sir. Let me take a moment of our time to thank our principal for taking time out of his very busy schedule and be with us. He has been a constant support and an encouragement for all the initiatives of ACCIC. And we also thank you, sir, for your continuous support in the future. Thank you, sir. Now, I hand over the session to Dr. Johnson Christadas, co-convener, Assistant Professor, Department of Microbiology, to introduce our speaker of the day.
Well, good evening. Am I audible?
Yes, sir, you are.
I hope I'm audible. Good evening to everyone. It's my immense pleasure to introduce the speaker for today, Dr. Padmadaraj. See, all of us, we have known X-rays as only a means of diagnosis whenever we get injury in our bones. But X-rays and crystallography has been a part of his life. So this is the kind of eye country that he possesses for his own self to get introduced to the world of science. And his publications that he possesses get added to his credits. Hello?
Yes, sir,
Hello?
you're audible, sir.
Yeah. There's some connectivity issue. I regret about it. So, in IGCAR and his areas of research is in the crystallography. It really fascinates me for his track record in crystallography because everyone knows about the viruses now. I think his introduction is very much needed as a crystallographer now because X-ray is not just a means of diagnosis in this world. Today, the viruses which can turn the world upside down needs to be crystallized. So, he is the scientist needed for the day. So, with this quick introduction, I request all the participants to extend a warm welcome to to the speaker. Sir, on behalf of the participants and everyone of the organizing committee and our college, we welcome you. Am I audible?
Yeah,
Yes,
Johnson, you're audible. So I think you can hand over the session to to Dr. Swarnadurai now.
Let me thank first you and God, okay, for giving me an opportunity to enter through my alma mater again, okay. So I also student of an American college, and I could see Dr. KJ was there, okay. I could see him. So it's my pleasure to interact with the American college first of all, okay. So thank you once again for giving me this opportunity. Okay. The
sure.
title yesterday I given like introduction to X-ray, powder X-ray diffraction, but of course I could speak about the single crystal powder diffraction like lava diffraction also, but let me restrict with the only powder diffraction. The reason for that is that even microbiology students are there in the audience. That's what you said. That is why I'm just giving one overview of the powder X-ray diffraction today. Tomorrow, let me just do some exercise on that single crystal diffraction also, like the lava diffraction and how to record the lava diffraction and how to index the pattern of the lava diffraction. All that I will do it tomorrow. So let me just start with this first slide. So, of course, you all may be knowing about Röntgen, who discovered the X-ray in the year of 1895. As soon as he was aware about that X-ray, then immediately he wanted to record a radiography or a clinical radiography of someone. He has chosen his wife, Annapata. You can see in the below Ranjan's picture, there is a skeleton of Annapata's hand. So as soon as he has shown this to his wife, she said very clearly, "Oh, I died because I could see my skeleton." That is the word she has used for the X-ray radiography for her hand. But now one of the cornerstone, and she has also took part of that cornerstone because without X-ray there is no lava. Without Ranjan there is no lava. Without lava there is no Brack and other people. Okay, so this is a story actually. So as soon as Ranjan recorded the first clinical radiography in 1895, after that only in 1940, Max von Laue, who has recorded the Laue diffraction pattern of copper sulfate pentahydride. Okay, you can see it's a very funny picture actually. Should be very puckered dots based symmetrical uh, pattern, but you can see that immediately you could conceive the idea that he said very clearly that something is there. He wanted to focus and then he wanted to make some more modification on the instrument which he has recorded and in fact successfully on zinc sulfide. He recorded a beautiful pattern and then he got the Nobel Prize for that in 1940. Immediately successfully to Max von Laue, the Braggs, that is W. William Henry Bragg and William Lawrence Bragg, both son and wife. They are Ranjan and Dhanapatha, husband and wife, here father and son. They got the Nobel Prize in 1915 for recording a funny spectrum of sodium chloride. You can see that there are some peaks are there. They couldn't understand what are these peaks actually. But they could understand there is some feature is that peaks. Then successively, finally they solved the crystal of the sodium chloride very interestingly, and they got the successful success origin from that over X-ray diffraction. So started with uh, Larvae, then ended up with bracts, that is polycrystalline material. So that was the cornerstone actually. if Raj did not explain about the power detection method, no one ever thought about solving the structure using power detection pattern, or it's called a polycrystalline. The technical word is polycrystalline because small crystals are around 5 micron. Okay, and that is giving more rings if you take near uh, photograph plate. Okay, so that we can convert it to river 1D. Tomorrow we will see about this how to record a 2D spectrum and then how to convert into one-dimensional spectrum and do the conventional analysis. Finally, Herbert Hooke and Jerome Carley, they got the Nobel Prize in 1985, and they worked on the phase problem. Most of you may not be understanding what is phase problem. From some experts in this field of X-ray diffraction, they may understand what is phase problem actually. We are only detecting the intensity, not the amplitude. Because amplitude means phase will come into the picture. So later you will understand what is phase problem. And also they developed the algorithm to solve the simple structure pattern uh, to solve the look at the actual crystal structure using a direct method. Earlier people used to do it with some um, heavy element method. They used to add some heavy element to the crystal. From that they used to get the structure. Instead of that, these two people made an entry into direct method, that is called direct phase structure analysis using a uh, single crystal. So these people are the well-known cornerstones of the entire field now, and nowadays each and every group like physics, chemistry, and biology, if you all combine all these three, I can call it, they say, material science instead of calling math, physics, chemistry, biology. So everybody's involvement is there. For example, this Herbert Hooke, he is a mathematician actually, and Jerome Carley is a physical chemist actually. Okay, they also worked on these problems and solve the structures. So this introduction, I will put next slide. So what is the nature of the X-ray? So it's very interesting to know about the X-ray. For example, um, nowadays people are talking about nanometer because of the nanotechnology. Earlier we used to say only the angstrom for the X-ray wavelength unit. Okay, so but nowadays people are talking about nanotechnology. We also get X-rays from 0.1 nanometer to 100 nanometer. Of course, this clear-cut division is there. It's not so actually. For example, some of the gamma rays may enter into the X-ray region. Similarly, the UV rays also enter into X-ray region. But generally, this one angstrom, this 0.1 nanometer means 1 angstrom to 1000 angstrom will be called as the X-ray region. So, okay, so this is here electromagnetic base actually. So electromagnetic theory people are well known about X-ray, but a little different actually. So a very interesting story is there. For example, we look at a story about Lave. Lave was discussing with Ewald. Ewald's you all may be knowing it. And this Ewald was working on some problem like theory of oscillations of material, particularly visible light with the interaction of the crystals, and he wanted to get some information about that. But this lobby suggested to him, why are you working only with um, visible light? My instinct says that you have to work with some low variable electromagnetic wave. So then he was not able to understand that. Then he explained him that shall I try this with X-rays? Then he was said, okay, we'll try to do something, X-ray for my theory. Then X-ray was, he has recorded the X-ray diffraction pattern. Finally, he got the Nobel Prize for that, but this man, he was lost the chance for that. Okay, so actually, he was executed this job with two of his assistants, Paul Nipping and another person. Okay, so this X-ray is a sinusoidal oscillating electric field with at the right angles a similar very magnetic field with changing with time. The other description is that particle nature of X-ray that's called photon. So this will be very useful for you that for the chemistry people like XPS. In the case of X-ray diffraction, we call it as a uh, they, the case of XPS, we'll call it as a photon because from K alpha, X-ray will be bombarded on the surface and from the emission they will get the electron. So there is a that is a photon, it is a particle. Okay, so in the case of X-ray diffraction, it is a uh, Day, in the case of X-phase, it will be a uh, uh, particle. So, wave particle nature duality of quantum mechanics is satisfied by these people. Okay. So, the wavelength and the of the X-ray, for example, all the electromagnetic radiations can vary its energy and wavelength. Here, lambda minimum, that is what is the minimum energy lambda that one excitive can make it given by this formula uh, that is 12.398 in the center volt 3 divided by volt, whatever the voltage we are applying. So crystallography or spectroscopist, while a few workers are adopt the nanometer in the type of answer, as I said earlier. Okay. So X's also exhibit particle properties. They can be described as a flow of photons carrying discrete amount of energy and momentum. This dual nature of the property of all forms of radiation and matter is comprehensively discussed in the theory of quantum mechanics. Why XRD? Why not electron? Why not neutron? So first, let us see the application. Then we will see the why we are talking about X-ray diffraction rather than neutron or the electron. Okay. So X-ray diffraction has acted as the cornerstone of the 20th century science. Its development has catalyzed the development of all the rest of the solid state and much understanding of chemical bonding. So here we can solve the structure and understand the chemical bonding nature, like potential development it can do anything if you want to do it. So properties of matter like under high pressure. So I want to see what is happening here. If material is applying a hydrostatic pressure, so high pressure, and high pressure is well as high temperature, low temperature. So what will happen to this material under these conditions? So similarly, properties of material under different. Sorry, I have repeated that. So this will give the input to the computer central studies like DFT based, density central theory based computation, molecular dynamics, etc. So application of in chemistry. Since the Gemini belongs to chemistry, I thought of preparing more slides for chemistry only, but I just mixed up everything. Okay. So for example, um, phase and phase purity identification. Just the record Excel spectrum, you can find its phase purity immediately using a well-known data. But there is an interesting problem people working nowadays, like high pressure community, high pressure physics community. That is, if you see that sodium metal under very high pressure, it will be very transparent. Apart from that, this NaCl only we have heard in our life. But nowadays, this you can see that there is a paper by Zhang and Akram Akram in Science 2013. They wrote prepared this combination like NaCl7, NaCl3, and Na3Cl, and Na3Cl2, Na2Cl. So many similar stoichiometry they prepared. And they saw the structure of this material. Like NaCl7, if you take it to the PM3, it's a cubic structure. Okay. Similarly, NaCl3, that's an orthogonal structure. Okay. As well as cubic structure also available for that. Similarly, Na3Cl, it will be having a tetragonal structure. Na3Cl will have another two structures, that is P4/M, that is orthogonal structure, and CMM, and that is another orthogonal structure. So these people, they developed some algorithm to predict the structure at high pressure. Particularly, they worked on many ionic solids, and they predict this structure and studied about their stability. That is also very important. So it was stable actually. But you may ask, what is the mechanism of this stability? So the mechanism is basically NaCl may be purely in ion bonding only. But in the case of, we go to say Cl7, so we not NaCl6 or NaCl8. It's not possible to form it. These people demonstrated how this NaCl7 formation, and they synthesized it at a high pressure. They studied and they put it in the science paper. It was a very outbreaking science, and it was also, what is that, very interesting problem to work nowadays. So there is a code called USPEX. So it can be combined with any density spectroscopy based codes, and then you can predict the structure. It's a challenging job for the chemist people. Okay. So then, since that some biology audience was there, I started putting this N-calypines, peptides, and oxytocin peptide and insulin. Okay, these also, for example, these are some 5 amino acids and 9 amino acids, and insulin is having 51 amino acids. Below 51, it will be called as a peptide. Above 50, it is one. It's a, insulin is a protein actually. So these also nowadays easily solvable with the laboratory-based excess source. Okay. So similarly, the pharmaceutical industry. For example, recently, you might have watched in the TV, there was a huge queue for the getting the remdesivir. Okay, so remdesivir is available in many morphologies. Some only one particular morphology is very stable, and it should be effective for the people. But there was a black market was going on with some other morphology based remedies. If you check it, it will be remedies only for the biology people. Take the extra of these two different original remedies and black market remedies, they will be different actually. The extra but will be entirely different actually. So you can also work on these type of problems for the microbiology people, and you can find what is the stable structure, what is the different morphologies, and how much dose one has to give it, whether you have to give it in intravene or muscular, intermuscular, or a tablet, or they can study using this XRD. Okay, it will be giving some input to you to the pharmaceutical institutes. Okay, so the properties, building blocks of amino acids are called amide linkage. So this is formula of any amino linkage. So one amino acid is bonded with another amino acid and it gives a type medication. So these are the applications of some limited application only I given. Okay. So what are the different X-ray generating forces actually? So X-ray can be generated generally by nowadays people are talking synchrotron radiation. So the electron will be oscillated near circular path. When the circular path is changing, the velocity is changing by changing its direction of rotation. So in particular beam line, they will be reflected with the proper undulator and modulator. They will bring it to a working place, and they will use and tune that wavelength for a particular application, and it can be used. Similarly, laboratory source. It's basically based on the Coulombic force, and which produces the excess the economics in our laboratory. So the weak and strong nuclear forces combine to produce X-rays. Of course, this is not very useful because the source will be very weak actually. Again, the gravitational force. For example, if you think about galaxies and stars, the galaxies when they are moving, huge energy is getting lost somewhere, and that gravitational force also can give X-rays. But it is useful only for studying the astrophysics or the type of cosmology. The type of people they can experience this type of X-rays, then they can identify the stars and they can find it. It may be useful. But for us, the second one, the laboratory X-ray source, which will be discussed here. Okay. So synchrotron are nowadays accessible by very good for a quality data. So in India, Indore, Madhya Pradesh, that Rajaramana Center for Advanced Technology, they have a very good synchrotron facility. So anyone can access it. So they need not hesitate to approach them. So if you approach any one of the station which is doing the proper work like for biology or chemistry or high pressure or low temperature, you can approach them and they will give you a chance to access the data, but you should not put the data in the dustbin. After I say such a struggle, you got the data, you should analyze it. That is the most important. If you just dump it, then there is no use of this all the efforts. So analyze the data and you have to make it the same application. That's all more important. So, so these 2 points, Coulomb-based laboratory X-ray and synchrotron. But of course, I am not going to discuss about synchrotron here, only about the laboratory-based X-rays. This is a schematic diagram for any X-ray tip, Born X-ray tip, for example. So this is basically based on the Coulomb X-ray Coolidge tip. They were working on the Coolidge tip earlier. So this is a schematic diagram actually. So here, this is the filament with a cup, this area, this yellow area. Okay, so this is the cup target. So any target we can use, which target for which application is determined. So then we can use accordingly suitable target. Here, this filament will be emitting the electrons. So these electrons will be get accelerated here. For example, here there is a cooling water is going inside and then it's going outside. This light blue color thing which I put it here. So here very important thing is that note down that here the acceleration voltage is minus 40 kV actually. So and this will be at zero because high voltage one cannot approach it so easily with the water. That is why we have put this as 0 kV and this is minus 40 kV. That is the circuit. So this is the modern X-ray tube actually. This tube we will put in a proper holder and then we will uh, take X-ray. This circle, whatever I have put it here now. So this is barely a window actually. This is very transparent to X-ray. For this, there is all the four windows are there, and this X-ray will be coming to that one, and then it will be focused using a collimator. Then it will be coming to the sample for analysis. So as I said, this is the barely a window. So this is uh, the executive folder. You can see this. Okay, this is the path this has gone inside from the left to right, and then this is the place where the cooling water is going inside. This is a typical experimental setup for a lava diffraction. I made it personally, and so this chilling water will be going inside, and then it will be traveling up to this point. That's the anode, and then it will come out, and then it will be cooling the tube. What the copper target, static target. If it is, if you want very high energy X-ray, then you have to go for different type of target. Instead of static, you have to go for the dynamic, like rotating anode generator. That will give you more energy, and you can use it for the particular for some low wavelength targets. Okay, so this is the actual experimental setup for a lorry. Here, that gonium, this is the goniometer, and this is a hole where we will insert the collimator, and then we will record the lorry. So this is a photograph of them. Is it audible now?
Audible, sir, but there is a noise.
Voice is not clear, huh?
There is some outside noise is coming.
Nothing is here actually. I don't know.
Maybe a fan is running.
No, no, I switched off all the fans. 3 fans also switched. Yes, we do it. Okay, this is the extension which is shown in the previous slide. Okay, and here also that chill water line is there, and this is the high voltage cable. Whatever I showed you with my mouse cursor. Okay, and here the X-ray will be focused on this particular point. This is a sample holder which will be rotating. This sample holder is made up of silicon 911. Could you understand? It's audible now? Hello?
Yeah, it is audible,
Ah,
but there is some gap between your talk and the thing.
okay. Can we get everything perfect? Okay, I try to make as slow as possible then. Okay, so this is X-ray tube, and X-ray will be coming from here to the sample. Okay, after scattering, it will be going to the detector. This is the entry point for the detector. Okay, so this detector is mainly made of a PMT tube. Next slide I will show you that. Here another type of what is that? Detector I have shown here. Okay, so there is a knife edge. You can see this small block point, which you can insert in a slot so that you can align the sample. Okay, so that this X-ray will be exactly falling on the sample, and you can get the data very clearly. Okay, this sample will be kept rotated. Okay, and this is a knife edge for the alignment. X-ray tube and detector. Okay. This is a photograph about the entire instrument. Like this will be there. It's in an open condition. Okay, so when you run the sample, you cannot keep it open. It will not generate X-ray. It will be shut down immediately. So just for photography, I have taken a opened up situation. Okay, and then I recorded this photograph. Okay. So now I'm collecting some data using this computer, and data is getting collected here. So this is actually a German-based instrument. The instrument name is TOE GmbH. Okay, TOE, but model is steady.
ரொம்ப வந்து ஆபாசமா பேசுவதாகத்தான் அவர் பேச்சு. அவரை பத்தி
What is it? Hello?
Nothing, sir. You can proceed. Some participant.
Okay, this is a schematic of the whatever I have shown as a photograph now. You can see this X-ray is diverged here. It's fallen on the sample, and it is there is a secondary monochromatometer. Okay, this monochromatometer is basically made up of graphite, and it is fallen on the another monochromatometer. Okay, so then it is falling on the detector. Okay, this is a schematic diagram of the whatever the XRD instrument we have just shown it. I have just shown it now. This instrument, okay. So the entire circle is around 520 nanometer. Right here you can see the specimen to counter distance. Okay, so this is the counter distance. I'll make it. Okay, this is the point. This whole circle will be 520 nanometer diameter. Okay, so target here is I have used copper K alpha, copper, and then this average wavelength of this copper K alpha is 1.5406 angstrom, and secondary monochromate is graphite, and this detector is actually made up of 4 kilo sodium iodide doped with thallium, and the maximum power we can go around 4 Kelvin, and but generally the operating condition for us is 40 kV and 30 milliampere. Okay, so specimen to counter distance is 260 nanometer, 260 mm, and 2 theta range. You can go from -2 to 167 degree actually, but data acquisition step size is 0.001 degree. Okay, and we can operate in theta to theta mode, that is called background mode here. Similarly, for omega scan is also available. This omega scan is for thin film, whereas normally this background is for the polycrystalline powder extract. Okay. If my voice is not audible, just interrupt me and tell me. Okay. So the interaction of X-rays with the matter is like when if you take a specimen, there will be always absorption. It will be made into heat actually. Then fluorescent X-rays will be coming out. Then ejected electrons will be coming. This electron will be photoelectrons, and Compton recoil will be there. Similarly, scattered X-rays will be giving coherent from bound charges, and incoherent Compton modified electrons will be there. Similarly, transmitted beam also will be there. Generally, most 90% of the interest will be get absorbed by the specimen. Okay, so only 10% will come out of the material for the diffraction. That only we are using for our sample characterization. So choices of the target. The choices of the target depend on a number of factors. So if you take copper K alpha, is a conventional X-ray because it was used to record the diffraction pattern of organic crystals in thin film form. Similarly, molten K alpha, it is used generally used by the high pressure community. Okay, for high pressure recording, they'll be using this molten K alpha. Sorry, molten K alpha. So if the crystal size is very large, like in proteins, lambda larger than copper K alpha is used. So what is that they will use? Let us see later. Then similarly, the elements present in the crystal play a role in the choice of lambda. For example, Organic crystal, if you take inorganic material, they will have a different type of interaction. So the choice of lambda is depend upon the material also. Finally, the atomic number difference between the target and the sample. So if you use some sample very close to copper, like iron, so iron will give a lot of fluorescence, so it will not give any proper diffraction. Okay, so similarly, elements flow below calcium is very little bit difficult because of the fluorescence. So here I made a tablet about a tabular column about the different targets like chromium 2, silver, and we have alpha 1, alpha 2, similarly beta and beta filter. What is the filter we are using for beta filter? And similarly, what is the critical voltage we have to apply at the characteristics? Okay. So, for example, this chromium, this K alpha 1 is 2.289, the larger wavelength, and if you go to this silver, it is 0.5594 angstrom only, that K alpha 1. Similarly, if you take copper, it's actually I have written it 1.54056, but we will generally make it as 1.5060. Okay, and this is a K alpha 2, and then this is a beta, and the beta filter for this is nickel with 15.2 micron thickness. Okay, and critical energy is liquid is 8.98, and maximum Q space. That Q space means that I just put it here. Q equal to 4 pi sin theta divided by lambda. Where 2 theta is the scattering angle, and the lambda is the wavelength of the incident X-ray. So this is the characteristics lines of the X-rays, like K alpha X-rays and L alpha, M alpha, like that it will be going, because if you see the what is it, EDAX people, any EDAX spectrum, so there you get a lot of K alpha lines and L alpha lines and M alpha lines. Okay, so here you just concentrate only on this K alpha 1 and K alpha 2. So you could see a difference between the K alpha 1 and K alpha 2 energy levels. Audible? Hello?
Yes, sir, you're audible.
Now, you could see the difference between the K alpha 1 and K alpha 2 energy level split. So K alpha 1 is coming from L3, and K alpha 2 is coming from L2 actually. So this is the reason that the intensity ratio between K alpha 1 and K alpha 2 will be always 10 by 5, or it is 1:2. K alpha 1 will be having higher higher intensity compared to K alpha 2. Okay. So the reason behind that is because it is coming from the L3, where more number of orbitals will be there, so that the more number of electrons will be coming from that energy level to the target, to the K1 orbit. And similarly here, that the number of electrons will be less actually in the for the K alpha 2. So the ratio between the number of electrons the K alpha 1 and K alpha 2 is exactly half. That is why this K alpha 2 will be having exactly 1:2 ratio of the intensity. Okay. So this is a typical molecular target continuous X-ray spectrum. You can watch here very clearly. At 20 Kelvin, the intensity is very low, and the short wavelength also at very high actually. When you increase the voltage of the tube, then it is shifting towards lower wavelength, and the intensity also increases. Similarly, as going to 50 kV, you can see the short wavelength is very low. That means higher energy of the minimum say, emitter, and this intensity also increases like energy. So that is coming from the this wavelength, this formula. So the X-ray peak intensity increases with the applied voltage. Similarly, the short wavelength also decreases with the applied voltage. Okay. So here you can see that there are two spectrum I have shown you in this graph. One is the copper um, spectrum, and this is for the molybdenum. You can see that there is a characteristics like K alpha, K beta for the molybdenum. Similarly, for copper also there is a K alpha, K beta. But this mainly we will be using this copper K alpha instead of the molybdenum. So these uh, spikes will be generally called as the characteristics, whereas there is still some background is there. If you are not filtering that, it will not be good for the X-ray diffraction. Because this is called the background radiation, or it is called the Bremsstrahlung. Okay, so the greatest intensity at slightly larger wavelength, uh, and similarly, X-ray spectrum shows a number of short spikes of high intensity. Similarly, the peak positions are changed from one metal target to another metal target. So these peaks are characteristic of the metal target. So how to filter this one? There is a general formula for that. For this is only for copper K alpha. This X-ray spectrum. Okay, so this is a copper K alpha. This is copper K beta. Okay, so if you see that this is around 1.4 angstrom, whereas this is at 1.5460. Okay, but if I'm putting a small nickel foil, it will cut off all these K beta, and it will be giving only the characteristic K alpha. But you can see the intensity difference, same scale, this y-axis, but the intensity of K alpha has also come down. That is why you have to be very careful in choosing the filter. The filter thickness also matters a lot actually. So generally this is this formula of me by rho mixture equal to x1 into mu rho by first phase, and then mu rho by the second phase. It will be extended like that. But here we have only one filter, that is nickel. So mu by rho is nickel equal to, so just me by rho of the nickel alone, you can take it here, and then you can make that nickel, and you can calculate. Then you will get this K absorption, absorption by the nickel, this me by rho, and its unit is meter squared by kilogram. So this sharp disconnect in the curve is called absorption edge. This edges, this one, and similar this one. Okay, so this is corresponds to the ionization potential of the K cell electron, and is called the K edge. They correspond to the entrance of the new absorption mechanism. So there is a mechanism by which they are filtering. The mechanism is because of this foil, that this absorption edge, which is very close to the K alpha 1 only, and that's why it will cut off remaining Bremsstrahlung and everything, and it will give a nice K alpha 1 or K alpha spectrum only. Still, this K alpha is having K alpha 1 and K alpha 2. So, detection of X-ray. Generally, the conventional way of any clinic which they are going, they will give in a photographic plate, that is film actually. The film is made up of some silver halides. Okay, so they will expose the object using that silver screen. Okay, silver current based screen, and they develop it chemically, and then they will bring out the image like Annapurna's hand. Okay, so and then this film is also used still now by the lava diffraction community. Okay, they are still exposing the sample with the uh, film and then they are developing it. But nowadays, so many new technologies have come, like two-dimensional X-ray detectors. One such thing is like storage phosphor screen. And then this is called as um, uh, imaging plate. This is made up of the same uh, polyester screen coated by barium fluorobromide doped with european 2 plus. And similarly, nowadays, this cadmium telluride, CCD based, and linksite, that is silicon pin array based, like that, so many area detectors come. Okay. Another interesting material is zinc sulfide. For example, when doing the experiment, before starting the experiment, for example, we want to align exactly this beam is falling on the sample as well as the um, beam stopper. So for aligning that, we will have a small screen which will immediately glow like anything. This zinc sulfate. As soon as the X-ray falling, it will give nice greenish yellow color. Okay, and then from that you can direct the X-ray. Another interesting area that is your human skin. Okay, you can also expose your human skin. Okay, you can feel the X-ray falling on you. For example, how much time they are giving for the taking a clinical X-ray radiography. It will be like a millisecond. Whereas if you just put your skin for some 5 minutes, that's all. It will give a very dangerous effect, like ghastly effect they call it. Okay, so be careful, be away from the X-ray always. It's not for threatening the people, but the people who those who are working in the area, they should aware how much dose they are getting it. That is why careful lead-based shielding they are putting for the instruments. Okay, otherwise it will be falling on a human. It will give nasty effect. So that's all. You cannot do anything. Okay, so they make irreversible damages on your tissues. Okay, so be careful. It's a beautiful. What is that? If you want to spoil someone, you can put them in the X-ray for some 5-10 minutes. That's all. The life is gone. Okay, so be careful on that. Then these are called area detector. Then I will move to 1D detector, the Geiger-Müller counter. Okay, so similarly positions and proportional counter, flowing gas proportional counters. These all are you may be familiar with your BSc level, Geiger-Müller counter and all. So they are used mainly in the industrial applications. But this position detector, it is very easily available in the market, and people are using still position detector for a range of two theta can be uh, data can be collected at a time. Then they will move the data. But the position detector will be flat. It will be like a curved because our X-ray will be coming in the curved path only, like a cone in the case of polycrystalline. So they will do some arc correction. That's called arc correction. Okay. So these are the another detector and the point detectors. So lithium doped single silicon or germanium crystal. It's also very interesting and very high resolution and uh, more sensitive detector actually. Okay, so it is almost 15 times better than a scintillating detector. Okay, but this problem is that it should be always immersed in the liquid nitrogen. Okay, otherwise this the detector. So always you have to keep it as a liquid environment. Otherwise, this will get spoiled because the lithium is easily flowing out from these crystals and it will get spoiled. Okay. him, I already doped by tell him. Already I told you this is another situation which we are using it because of the easy accessibility and high emission efficiency. Okay. So many exciting instruments available in market. If you have any idea, you can purchase one of them. So like Ricardo Smart Lab multipurpose X-ray diffraction and Penaltical, Bruker, Toei, Siemens, Philips, Seibert, Natsu, Olympus. Okay, of course, synchrotron also you can add in that one. But synchrotron you cannot get it like box. But all other things remaining 9 things you can get it as instrument for your lab easily. Okay, every instrument is having its own advantages as well as some disadvantages. For example, if you take Bruker, the GATS director, the general area directed diffraction director system. So that's the director they are using it. That will give very nice spectrum. For example, I have here alloy, which is having some 2 or 3 phases. Okay, then I want to focus on a particular phase. Okay, so you can collimate the beam of that Brooker's source, direct source to some 50 micron level. Okay, and you can record the XRD for that particular grain only. Okay, and from that you can solve the structure of the one phase which is available in the alloy phase. Okay, similarly, this TOEI, another very interesting machine which we have. TOEI is actually it is stand TOEI steady and P for powder. So even though they made it for powder diffraction, these are the people, they are very advanced people in the field because more than 120 years they have done in the field actually, the Siemens people, German based people. Okay, Philips expert product hardy. And this Siemens, I have written somewhere. Yeah, Siemens T500 5000. It's just a huge circle-based instrument. It can be adapted for liquid, not liquid, which is for cryogenic environment like CCR-based, closed cycle refrigerator-based instrumentation. And you can put the sample in the middle using that instrument, and you can record the low temperature study for your sample, even from 2 Kelvin to temperature. Okay. Similarly, this Siemens also having high temperature attachment. Up to 1200 you can go. So imagine when you just put a sample on a sample holder, the sample holder also will be having a special sample holder. Not just like that, any sample holder you can use it for the high temperature. So molybdenum, they will generally use it for the loading of sample. So molybdenum will not give any background or it will not use its peaks. So it will give only the sample peak and peaks. From that you can study its high temperature property of the sample. Okay. So Simatsu, another very interesting. So many in situ properties you can study, like applying high, not high pressure. High pressure, if you want, you have to go for diamond and ultrazone. The different way of working. And here that like you compress the material. Okay, like if you want to see the strains on the material, then you can use this mass. So like that, in grazing is an angle. There is region of interest only I can study. For example, I may bombard my material with some metal or some gaseous particle, some other dopant for a particular depth. So depth I can calculate very easily using a code actually. So from that I can fix my instrument. Okay. So the region of interest or depth of probing. Okay. So depth of probing is depending on the instrument. So this symmetry is having nice arrangement for the thin film also. So of course Olympus also one of the interesting magazine like a bench job, but it's only just for the whether my case is pure or not. Nothing else can be done on that. So of course it's being a singleton beamlines. Can you guess what is this looks like? Actually, this 2014, 2012 was the 100th year of the Nobel diffractions discovery. Okay, so to celebrate that, NASA sent this instrument to Mars. Okay, so this instrument collected the samples, and then it was sending the samples through this funnel type of thing, and it sent inside and then recorded the XRD and sent it to the NASA station. So people at NASA station, they analyzed the samples, XRD samples, XRD pattern of the samples using this data. So 2012 they launched it in to Mars. So this is an XRD machine. It was running on some 6 wheels, and then instrument is sitting somewhere inside the cabinet, like uh, heavy vehicle tank, like that it looks like. So this is very small in size actually. Its name is called Cheming because it's mainly sent for the chemistry and mineralogy. Okay, on the Mars surface on 2012 actually. Okay, so this is mainly to celebrate the year of 100th year of the Lowry diffraction. Okay, so now the director part little bit I talked in the previous slide, but actually what is happening when Excel is falling on the scintillation director? So this scintillation director will be generating some emitting light using this what is it called photocathode. Okay, so generally this photocathode will be cesium antimony. Okay, and this will be emitting the electrons. Then successively, because of the application of so many things are there. These are for the different voltage setting for the PMT. Okay, so this is the PMT actually. So it will be enclosed in a smaller cycle or bigger size. This is another type of completely covered photo, sorry, X-ray director. Okay, for the XRD diffraction studies. Okay, so inside that this type of this type of PMT glitcher. Okay, so this is the mechanism. So this is another phase diagram. For example, here the high voltage will be applied here for the diodes, and then the high voltage divider will be there. That is, these pins, whatever you are seeing in the rightmost picture, no? That they are the who are applying the different high voltage. So high voltage, these are mainly for the high voltage divider, mainly the assembly of resistors. That's all. Okay, and then the uh, light screen, and then photoelectron, whatever coming from the crystal. Okay, so second electrons. So finally it is coming and collected here. This is a data acquisition system. Okay, so actually it will not come like a pulse. It will come something like this, very, what is it, Lagrangian, but not Lagrangian, what is it called? Lorentzian type of peak. So this peak now you have to modify it, and then you take the amplitude and collect it for some time. Then you have to make it like a perfect what is it, square pulse. Then you have to send it to the counter. From the counter, it will be coming to the PGS data. Okay. So this is the schematic diagram of the what is it? Excel directory which we are using in the laboratory. So this is a well-known picture for all of you. So for example, this generally people write 2D sin theta equal to lambda, but generally instead of writing that, you can write it like 2D HKL and then sin theta lambda equal to lambda. Why I am saying that n is playing no role in the X-ray diffraction of polycrystal materials, whereas uh, instead of putting it like n alpha, you just put lambda, so that 1 by DHKL. So this is DHKL, this is 1 by DHKL equal to 2 sin theta by lambda. lambda. This has some meaning actually, which we will discuss later, but you just remember this is called the reciprocal lattice vector. Okay, so for example, your direct lattice, you write your translation vector equal to UA plus VB and plus C. Um, what is it? UA, UBW, right? UA, VB, and WC. Okay, like that you will write your direct lattice translated vector. So similarly, this reciprocal lattice vector, you will find it very easily for the polycrystalline material or for any material, for a three-dimensional material, like A equal to B cross, that is capital A equal to small a cross B, B cross B divided by volume. Okay, that is the way you will write that reciprocal lattice vector. So this reciprocal lattice vector only playing a major role in any crystallographic studies. Okay, for any structural analysis and any data collection and any phase problem, all that you have to use only the reciprocal lattice vector. Okay, so this reciprocal lattice vector D star, it can be written as reciprocal lattice consider vector, let us assume it's G, then equal to H, that is millimeters, H and capital A vector, plus K, capital B vector, and L, capital C vector. The ABC are the reciprocal lattice vectors. Okay. So this is the nice picture about the uh, information about the reciprocal lattice space and reciprocal lattice vectors. For example, this is a circle, the crystal is centering, and this is centered, placed at the center of the circle. When the this is the X-ray beam which is falling on the uh, uh, exactly falling on the crystal, and the emanating uh, X-ray is this point. This point is called 0, 0, 0 position. Okay. So and then 1, 0, 0. So whatever inside the crystal will be called as the um, direct lattice space. Whatever outside this circle, okay, that is I'm calling it as my reciprocal lattice. Okay. If you slightly rotate in the crystal, the reciprocal space associated with the crystal also be rotated. Okay, for example, here B star and B star and my A star, they were like this actually. But here you see this A star also rotated. Okay, so this is what Ewald told in the beginning, but he could not get that idea in the beginning, but Lave got the idea. Okay, so this was explained by Lave. Sorry, Ewald later. Okay, so when this particular point, this 230, okay, this Miller indices is 230. When it is falling exactly on the circle, then it will give you a diffraction point. Okay, this is not falling, the next one. Okay, so 100, 200, like that it's going up. Similarly, the other side also you can think. Okay, negative side. Minus 100, minus 200, right, that you can see. Similarly, this here it is 010, 020, 030. Only in 2 dimensions I have given the reciprocal lattice. Okay, so this will be very useful for future studies. Okay, that's why I'm just giving this picture. So of course, I said that high pressure and applying high compressing force, expanding force. Okay, so how the peaks will be moving. For example, this is the exact peak position. This one, 2 theta, for a d naught. Okay, that for this particular d naught value, this is the peak. But if you stretch the uh, specimen, Okay, what will happen if you apply some strain on that term? So you can see that when you stretch it, that this d naught will be varying. So when d naught is varying, and the peak is shifted to the left side, that is becoming higher value. So 2 theta will be reduced. Similarly, if you apply a non-uniform bending of the crystal, what is happening that delta 2 theta will become minus 2d 2 delta d by d tan theta. So this is the way to be bending, and its intensity of the will be reduced. But because of the uniform bending in both the sides, the peak position is not changed, but only the uh, intensity is reduced in the case of bending in the uniform bending of the both the sides. Okay. So this is one of the data which I have shown here. You can see this is going giving one as per this Bragg's law. Just to give only the peaks like this, very sharp. It should not have any broadening and all. Okay, but reality is it like that. So this is exotic pattern of some thin monoxide. Okay, so there is some peak here. So with 100% intensity and 110 another peaks here. That here so many peaks like 3 peaks combined together. So these are the well established data, and data is available for thin monoxide. So if you see this as a single wavelength and d value. D value alone is varying the y-axis, and lambda is constant. Okay, so you have to get a pattern like this stick pattern, but actually we are getting a pattern like this. That is the pattern we have having certain full width of maximum every individual peaks. Okay, so why this pattern is happening? That we will see the reason, and we will try to understand what is the cause for this uh, broadening of these peaks. So this is the combined XRD pattern. This is a as such obtained XRD pattern, and this is the XRD pattern with the stick pattern, that is the delta function pattern. Okay, so here that XRD line broadening can form from many sources. They are listed below. Instrumental broadening. Okay, for example, this is DI, is an instrument broadening, mainly because of the unresolved alpha 1, alpha 2 peaks, like K alpha 1 and K alpha 2 peaks. And similarly, um, uh, non-monochromaticity of the source, finite width of the alpha peak. If the peak is not monochrome as well, then in that K alpha 1, K alpha 2 will be merged at the low angle, whereas in the higher angle, they will be well visible. Okay, and similarly, crystallite size in the vicinity of the Bragg 2 theta, the negative of the Bragg's equation being satisfied. That is, the constructive and destructive will be there now. That because of this big broadening, and because of that crystal size, so that will be some deviation of the from the perfect Bragg's law. So that will give some interference, which will give the effect, that is intensity distribution. Similarly, strain. So resistant strain arising from the dislocations. So coherent precipitates. These are the things may be possible actually. Similarly, stacking fault. Okay. So in principle, every extent possible, the contribution to line broadening instead of a delta function. So it will be a function of this BI, BC, DI, and BSM stacking point. So here you can see that the full width of maximum, how it is varying with respect to different things like the left side is diffraction angle, and then intensity is of full width of maximum width, and this is actually fitted by several functions. Okay, for example, this is a perfect delta function, and this green color is because of the red one is the attained peak actually, and then this green one is the crystalline size effect, and then this light blue color one is the instrumental effect. Okay, so the diffraction peak which we see is a result of various broadening mechanisms at work. Okay, so as I said, strain, crystalline size, and here I have listed out very clearly instrumental, crystalline, strain, and cycle. So if you want to get the full of maximum completely, these are the things: instrumental, crystalline, strain, and stacking part. All that you have to add. So here I have given some notes actually. Inherent asymmetry of many pole direction profiles. So any different profile, if you take, they will not have any what is it called, symmetrical. It will have some asymmetry in their profile nature actually. So it gives hindrance in the external in their application in the various studies. Okay, so beyond the phase and there is nothing in between because of this asymmetry in the profile. So how to overcome that? That we will see. Okay, the specimen's shape contribute to the observed profile. So deconvolute from it allows it to see the insight in the anisotropic strain of the crystallines. So if you just deconvolute the um, shape into the instrumental part and the specimen part, then you can see the in specimen part alone. Okay, so similarly, the most exciting of the profile fitting developments have been counting the development of whole pattern X-ray refinement. That is like a ritual refinement, which is a starting point, which you can give the um, percentage of the phases in atomic as well as sorry, in volume as well as in atomic percentage. Okay, so from that you can get the volume fraction by rito refinement. You put more than up to 8 phases you can put at a time in the uh, fitting, and then you can find uh, volume fraction of the sample. Okay, what are the phases exist in the sample? So this is all started by the Reed Weld. Reed Weld wrote a program for essentially fitting the uh, neutron diffraction patterns. Okay, but it was finally extended only for X-ray diffraction. Still, there is no ritual refinement for the electron diffraction, but X-ray diffraction people are adopted well, and it is left and right people are using this ritual refinement for uh, studying the crystal structure. Okay, so the normal symmetric Gaussian nature of the neutron diffraction profile has aided the application of this method to develop its current rather matures. So we'll see what are the other profile which is existing. Okay. So for example, these two are playing the major role in the XRD pattern. Okay. So take a profile which will have these two components. Okay. One is the Gaussian. So it is formula I have given here, and Lorentzian. Lorentz formula also I have given L of z equal to y naught divided by 1 plus z squared m the whole power of m, where z equal to 2 theta minus 2 theta particular degree, that is the broad angle, divided by beta by 2. Beta is the fluid top maximum, and for example, if 2 theta is the peak position and beta is the fluid top maximum, I naught is the peak energy. That is if m equal to 1. So if m equal to 1.5, this is called intermediate Lorentzian. If m equal to 2, this is called modified Lorentzian. So this z is multiplied by 4 into 2 to the power 1 by m minus 1. Then the function is called Pearson 7. Similarly, Pearson split Pearson is there, and so many other functions are there for fitting the X-ray diffraction. fitting the peak to extract the information. So this is the full width of maximum. Already we have discussed about this one, but keep it here. Instrument, crystallite, and brain and structure factor. These are the factors you have to keep it in mind, and then you have to apply the profile accordingly. Okay. An important point to peak broadening is the fitting of the profile to the peak. The standard functions we use generally are Gaussian Lorentzian, or the combination of these two is called the other functions, like it's called pseudo white and PMS7. Generally, this B equal to, that is full width of maximum minus this instrument broadening is equal to big broadening because of the slides and strain. This is equal to BR. This B crystallized plus B strain will be called as BR. Okay. So here you can apply the Lorentzian function of this form. Okay. So here this BI is instrumental, and already I was told about this BI is because of the instrumental, and BC is the sprite, and BS is a strain product. Okay. So here example, for example, this take this peak. This red color one the observed peak, and then this green one is the fitted one, like with Laurentian, and actually mm, this is not fitted actually. This just like it is shown like that, Laurentian and Gaussian. It was trying to fit the external pattern with Laurentian. Okay, but Laurentian will always having a longer tail compared to Gaussian. Gaussian will be having more symmetry in it. Okay, so delta is the ideal function actually, and crystal size this like this peak, and then strain is circular line actually. Okay, and instrumental also inside it is there. Okay, overall the for a peak with Gaussian profile we can write it G of Z equal to I naught into exponential to the power of minus ln2 into z squared. Z also we defined in the previous slide. This is the Z. 2 theta minus 2 theta not dot, and divided by beta by 2. And this is actually other functions, like for example, this is a measured peak, this green color one. Okay, so this peak is fitted with the combination of this Laurentian and Gaussian. Okay, so the combination is called as this is called actually Y function. Okay, this type of Laurentian as a function of x by beta I plus g of x by beta g, that is this is for instrumental, and this is for the Gaussian function. Okay, this is called just addition of these two functions. Okay, so it's called a void function, but generally people will not use this void function. People will be using this pseudo void. P stands for pseudo, a pseudo void. It is very similar to that this one only void function, but here um, P as a function of that is x comma instrumental broadening and Gaussian broadening, it's equal to eta star, then the function of Laurentian function plus 1 minus eta star Gaussian function. Okay, for example, if this eta is playing a major role here, if this eta is slowly decreased and it's becoming sorry, slightly increasing, and it's becoming 1, then you get only Laurentian function. Otherwise, if it is keep increasing, you will get the uh, Gaussian function. Okay, so if it is eta is increasing, you will get up to 1, let us assume. Okay, then there will not be existing any Gaussian function. Okay, if eta is equal to 0, then Laurentian will be disappear. Only Gaussian will be here. Okay, This is just not just addition, actually the convolution they will do it, but for the simple understanding, this is the way the pseudo-white function is behaving. Okay, for example, this is one observed tooth that peak actually. Okay, so you can see that this peak is measured is at measured, and then this is fitted with Lorentzian, Gaussian, and then pseudo-white. Okay, pseudo-white is not almost visible. You can see this tailing here. Similarly, this tailing here, this is green and red, black. That is pseudo-white. They are almost matched. So it is not only for the readable refinement or not only for peak fitting in the XRD pattern, it is applicable for any peak fitting like you have a Raman peak or you may have some spectroscopic peak, then you can use all these functions. Okay, so to fit and extract the exact position of the peak position. Okay, apart from that, it will give the full width of maximum and it will give the area under the curve. All this also very important for the analysis. For example, if you take the phase analysis, the area of the curve plays a major role. Okay, so this is about the white function. That is white function and pseudo white function. So L is the Lorentzian here, and then G is the Gaussian. Okay, L is, and this is all about the wide and pseudo wide function. Okay, so another powder XRD pattern. This is an interesting XRD pattern actually. So this is actually called dimethyl ammonium metal formate. Okay, so if you take just M and alone, just forget about this zinc here. Okay, what is happening? I have taken the crystal, recorded as XRD pattern, powder XRD pattern. You can see these two peaks, no? They're well overlapped with the polycrystal material. And these peaks, 1, 2, 3, 4, also very important actually. But there is not a signature of single signature of any peak rising here because they are from the different planes. Okay, so the single crystal means they will give, if it is 110, then 220. This will be 220. That is the set of planes only be appeared in the powder crystalline. Okay, for the single crystal. Okay, so just for the testing only I have taken this, and then this is for the dimethyl ammonium. Manganese 0.95, zinc 0.5 format. Okay, so you can see the difference between the single crystal and polycrystalline sample of the same material. Okay, so why this is arising? This peak is not coming up in the single crystal. So just see this is well oriented for this 100 direction. That is, this horizontal plane is 100 plane. That is, it's Miller indices HKL equal to 100. Okay, then its orientation direction is 100. So 100 peak has come. Whereas if we take this 110, this peak is still it's not having any bending. Okay, so it is having straight and it is like this 100. So there is no back scattering from this, and that's why it's not appearing here. As I told in the previous case, here this peak has not appeared. This peak has not appeared. Okay, only this peak and this peak has come. Okay, the reason is they are oriented in a different direction. Whereas this 1200, 100, 200, they both have the same type of orientation. Okay, that is why this 100 plane is coming and 200 plane is coming. Whereas this 110, 111, and 210 peaks are not at all coming because of this uh, uh, track condition is not satisfied in the case of this crystals. Okay, this crystal. Whereas it is satisfied in the case of this crystal. Okay. So, for example, see the polycrystalline nature. So 100 there is some material is there with that orientation, so it is coming up. Similarly, 110 it was not coming in the previous case, but now there is a sample. Okay, this sample, this even though it is filtered, this crystal surface, not uh, grain surface, not the uh, cold crystal actually. To take the grain, this grain, which is having some interaction with this one. Okay, this um, what is it? That particular axis, 110 axis. Then it is giving up that peak. Similarly, 200, you can see that. So other peaks are also coming because of the polycrystalline nature. For example, if you just take uh, single crystal, you'll get only few dots. Okay, in the lava diaphragm. If we stack so many other things and overlap them in a different direction, then you'll get the dots in a circular manner. Okay. So crystal size and strain. So actually, it was expected as a delta curve, but it is not so. So the reason for that is Dak made the equation with the following assumption: crystal is not perfect. Crystal is perfect and infinite. That is the condition Bragg applied, and then he made this equation. But we have to modify it uh, uh, like for a particular HCl plane, we would write the equation. Okay, so incident beam is perfectly parallel and monochromatic. That is the assumption Bragg is made, and then he wrote the equation. But it is not so like that. So there are also deviation from the assumption on uh, the generating powder patterns. Crystals may not be randomly oriented. For example, uh, so many ensembles should be there in all other directions, but only few are there. And means can include give all the peaks. Okay, so similarly that the powder sample should be less than minimum uh, zero point 0.5 micron, that powder sample size. Okay, that then only you will get a very sharp peaks, nice peaks. Okay, so Sharpe formula. So this is for an assumption like a Sharpe formula used for the determination of grain size from the broadening and the peaks. Um, this was best for the Gaussian line profile and cubic crystal, not for all the other crystals. So people generally use for any crystals, like crystals like even for monoclinic also they will use this formula. But mainly this formula, this L is the average crystal size, which is suitable for cubic, not for any other thing. Okay, it is written like this: beta c. Beta c is the uh, full width of maximum of the crystal. Okay, L is the average crystal size. Okay, so K is a constant, lambda is the wavelength we used for the what is it for polycrystalline material. Okay, so you have to uh, separate out that strain broadening and crystalline broadening. Okay, so for that this curve, for example, this is turn theta. Okay, and it is plotted against the uh, 2 theta. You can see that it is increasing like this. Suddenly it is above 80. It is going up like anything, and from this you can find out that beta s strain is equal to, because of the 10 function like this, and then strain is in the material. Okay. Similarly, this is crystallite. So combinedly, this strain and crystallite, okay, you can see that smallest angle should be used to separate the strain and crystallite, not the higher angle. So even up to 100, you can use it comfortably, but less than 50 is more comfortable actually. Then you can separate out the crystallite part and then the strain part. Then you'll get what is playing the major role for the broadening of the peak. Okay, and this is actually another interesting thing actually. So BR, that is, as I have told, that the combination of strain and crystalline size BR. BR will be given by this formula BR equal to theta tan delta plus K alpha by L cos theta. So similarly, this can be modified and then it can be written like this. If you plot this graph, that is dr cos theta versus the sin theta, you can see this K alpha by L. That is the crystalline size actually. So larger the intercept, smaller the crystalline size. If the intercept is going up like this, then you will get higher crystalline, lower, smaller crystal size. If it is very low, then you get a higher crystal size. Okay, so larger this will be the in what is it, intercept. Here that it's called y equal to mx plus c. So this c is the intercept here, k alpha by k lambda by L. Okay. Similarly, the crystalline broadening. Okay. So that is in a special case actually eta will be 0. There will not be any body that strain will be there. But generally this PR cos theta, that is this one, strain the strain and crystalline combined. It will be like this. Okay. So this L will be going on in increasing without any end up. So it will go almost to the infinity, like a straight line one. Okay. So generally we cannot use this formula just like that, but some meaningful that BR cos theta by sin theta, and you can take within a range, and this crystalline size, and then this strain. Okay, just this you can differentiate from these two, and you can get the uh, information from the curve fitting. So far we have discussed up to the, what is it called, right, broadening of the peak essentially. So Excel generation, then detectors, and then what, how to convolute the peak, and then extract information like strain and strain broadening and extract crystalline size broadening. Okay, so all these things we have discussed now up to now. Tomorrow, just I will see inform you about how to identify the cases for the unknown crystal, or no, it may be existing, the database may be existing, but you have to choose it correctly. Otherwise, you cannot get it just like that. Okay. So tomorrow onwards, I'll discuss about this one. With this, I will stop today because almost going to be uh, 2 hours now, I think. 1.5 hours. I don't remember the time now. So tomorrow I will talk about the phase identification from the ICDD database. Okay. The ICDD stands for International Center for Diffraction Data. It is then in US, Penn State, okay, Pennsylvania state. Okay. So tomorrow onwards I will talk about the how to analyze the data using the database, existing database, and how to analyze the data for there is no information about the uh, information about the particular sample, how to proceed for the determine the crystal structure from the non-existing data. Okay, so standard data. So these part I will discuss tomorrow. Okay. Shall I close it now? Hello. Hello.
Yes. Yes. Johnson, sir?
Yes, ma'am. But I get some echo.
If you have some
If
questions, you
anyone
can ask
can
me.
answer.
Tell
Hello?
tell me.
Sir, can you put off your speaker?
Yeah, my speaker is on only.
Okay.
It's not audible.
Yeah, but I get the echo of my own voice.
Oh, here there is no problem for me. This is perfect for me.
Anybody else having a speaker beside your microphone? Please.
This is the, No, nobody's put it.
Okay, I regret if there is any technical glitch.
No problem.
So can we have a few questions if there are some questions from the participants, ma'am?
Okay.
Any specific questions from the participants to be clarified by the speaker? Well,
I would like to ask a question.
yes, ma'am.
So you were discussing about the effect of uh, stress or that is the effects. Johnson, I think your mic is the problem. Yeah. So you were discussing about the effect of strain on the peak shapes. Okay.
Okay.
So suppose if we wanted to decide about the particle size using XRD, should we really spell out to the person who is going to record the spectrum? Because there are a lot of other factors like instrumental broadening and monochromator. That problem also brings in shifting of peak. So many things you were discussing. So, but being a researcher, we don't know these problems and other things. You'll just pack our sample and send it to the for recording the spectrum. So, if how do we know that this broadening is because of the intrinsic property of our sample, or it is it is something with respect to the instruments? Because many times no we send lot of samples and there will be a uniform broadening in all the samples, though the chemically those samples are different. These are some experience from experience I'm just asking this question. So how do we rule out that because from the user end we will receive only the data, and just by looking into the spectrum how we can decide this is intrinsic to my sample, this broadening is, or something related to the instrument? You please unmute, sir. We couldn't hear you.
Now it is clear. Actually,
Yeah.
this instrumental broadening is the norm. Generally, this company fellow who is supplying the instrument, they will provide some standard data from NIST, National Institute of Standards and Technology at the US. Okay, so like lanthanum hexaboride, okay, and that PbI2. Okay, so like that silicon uh, samples. So many standard samples available actually. Okay, from these samples they record it. They will expect the well-known positioning of the peak. For example, if I want the peak of lanthanum hexaboride at a particular 2 theta position, if it is deviating, then it is you have to align the instrument properly. So these instrumental parameters one has to give supply to the user. Okay, so these people who record this X-ray pattern, it's not X-ray spectrum, it's a X-ray pattern. Spectrum means only the white wavelength. Okay, so pattern means from the material. Okay, so this X-ray pattern one has to, along with that, has to supply the instrumental parameters, like what is the slit width, what is the monochromator they have used, and what is the size of the monochromator. All that they would supply to you. then only you can do even the retail refinement, you can do based on that one. So every instrument will have its own instrumental parameter. Okay, so from that only you can just subtract the instrumental broadening as well as sample broadening. For example, you take a material with some, let us assume that you have a diffraction of 2D sin theta equal to lambda. Okay, so this d value maybe slightly changing, like changing for the second plane. It may be instead of 1 lambda, it may be 1.00 lambda, 0.001 lambda. Okay, so if it multiply by 1000, what will happen? It will be 1.5 lambda. So it will go out of what is it called? My uh, uh, back line. Okay, so it will lead to some interference, destructive interference in it. Okay, that is why you're getting the peak like uh, tailing and the unsymmetry shape. That is because of the sample as well as the instrumental parameter. Okay, so you have to get the instrumental parameter carefully. Then you have to use it for your analysis. Then you get your what is it called perfect fitting. Okay, so far I have picked up only one peak. From that, what is the information I have told you. So here after I tell about the whole pattern fitting. That is called read well refined mind. Okay, so many codes are available. We are using GSAS, general structural system analysis. Okay, so that code we will be using. We are using regularly for even organometallics. Okay, as I mentioned, dimethyl ammonium um, metal format. Okay, so we are regularly using our instrument parameters along with the refined code. Okay, then I'll get which of it is dominating, whether this instrument programming is dominating or the material property is dominating. Okay. You got the
And one more question. Yeah. The peak broadening, uh, you can decide about the size of the particles you are talking about.
yeah.
Now, what about the nano sizes?
Non-sizes generally the peaks should be very broadened. As I told you that the polycrystalline sample size will be around microns. Okay, it will give a short peak. Okay, if it is very broadened to one, it will be more sharpened. Okay, so whereas the nano material it will be giving, even if it is a bulk nano. Okay, don't worry about that. It will give you a peak with the broadening. Okay? More broadening of the nano.
So, can I take it like this: as the size in decreases, the broadening increases?
You cannot just like that take it. That's what I'm saying. You have to fit it and
Okay.
identify it, then only you can. So instrument parameter you should get it. Okay, and try to put it. So both the Laurentian will be there, Gaussian will be there. In the I always use only the pseudo white. Okay, the pseudo white will be giving the best fit. Simple. So generally this DPW is another way of code is the for ritual refinement. There people will be using the what is it called PSS split. Okay, that is another function. Okay, so that people will be using. So you have to use pseudo white and the more opt for any refinement and peak, particularly peak fitting of any spectroscope. This is not a spectrum; it's a pattern actually. Because of the so many parameters, it will like a spectrum. Any other question?
Sir, I have a.
Ah,
So you talked about the Schumpeter's formula and the crystallite size broadening.
not I could not get you.
So the Scherer's formula
Ah,
and the crystallite size broadening.
yeah.
So is there a relation between formula on the full width of maximum? Can that be mathematical?
Hey, mostly the people who contributed for crystallography is mathematicians. They would honestly accept that. Okay. They
No,
would.
no. My question: the Sherr's formula
Ah,
that you mentioned, is it mathematically related with the full width of maximum?
full width of maximum.
Are they related with each other?
Yeah.
Can that be mathematically related?
See, full width of maximum, as I told you, instrumental broadening, okay, then crystalline size broadening, uh, stacking fault, all these parameters we have used, included in that one, okay. So totally only they are forming the exotic peak actually, okay. So when you consider for the, what is it called, crystal size, okay, you have to be very careful in choosing the beta value, that is the full width of maximum, not full width of maximum, okay. So generally you have to take, what is it called, uh, crystallite paste. That is why you have to separate out instrumental broadening, stress broadening, okay, and now step instrumental as well as crystallite broadening. These two have to be separated out by fitting it. Got my point? Instrumental
Okay,
broadening,
thank you, sir.
no, instrumental broadening and the sample broadening. These should be separated out by fitting using a proper formula. Like as I said, what is it called? Pseudo white function, let us take. Okay. Then from that you have to take only the crystallite part. Okay. Which is which will give the peak value, full width of maximum. That you have to use it. Then you will get a proper crystallite size. That's what I told you.
And for naturally available crystals and biological specimens,
Natural available.
crystals
Hmm.
from the biological, that is like the protein molecule.
Your voice is breaking actually.
I'll turn off the video. So, can you hear me properly now?
Yeah, yeah.
Okay, regarding the protein molecules that are being crystallized and solved using X-ray.
Okay.
So, they are having a natural crystalline form when they are kept in aggregation. So, do you go for altering the structure of the crystal in order to image it?
No, no, no. You cannot. The question is I could not follow it, but the protein crystallography is a big
Yeah.
molecule. No, it's a single crystal. Okay. So if you take single crystal XRD, as I showed you in one of the sample, which is uh, a single crystal form as well as the polycrystal form. For the same, I showed the powder XRD pattern. Okay. Set of planes only coming in the single crystal uh, XRD. Okay. That is single crystal sample. Okay. Whereas if you powder the crystal, so many other planes are already coming out. Okay. In the case of protein, it is very huge in size actually. So I have to do with at least the minimum like silver target. Then I can get some information from the protein molecular crystallography. Tomorrow I saw some papers about that. Okay, I have some papers I read it. Okay, but generally we are not doing any crystallography of what is it called proteins. But, since
Okay.
Dr. Jemima was suggesting that some microbiology people also will be participating, I have read some papers and I got some powder pattern of these peptides as well as this what is it called protein also. Okay, That I will show you tomorrow. But as such, if a single crystal will not get any other paints other than this set of paints, family of paints. If it is 100, then it will go 200, 300, like it will get 4. If it is 110, then 120, 220, 300, 440, like that will come. Okay? You not get any other paints, family of paints. Okay?
And sir, X-rays are used in imaging techniques in medical field for diagnosis. So, how is the dosage measured there, and how we are assuring that safety to be used in diagnosis? You said exposure to X-rays can be harmful.
Okay, nowadays, if you go to any X-ray clinic now, they don't have any old film-based technology. Okay, that they have completely avoided it now. Okay, so they are using imaging plates. It's called a digital, uh, uh, uh,
Computerized
not computerized,
tomography.
not tomography. Tomography is entirely different. They radiography. Okay.
Okay.
In the case of that conventional, you will be using only what is it called film, on which the silver calyx will be coated on a polymer sheet. Okay. But nowadays, people are using that. For example, just go to any hospital now, they will see the radiography on the monitor. Okay. Not like putting into film on a light and then see the bone structure. And also this clinic radiography or industrial radiography, instead of yeah, what is it, black and white picture, you can get a colorful images also. So, for example, if bone is fractured, then it will be very well visible. For example, in the case of Annapata's hand, the ring was very visible. Okay, but uh, what about the tissues on the hand? It's not visible, no? So, for example, there is a physical damage on the hand. Okay, so nowadays, if you plot it as for the uh, a color image, okay, you can bring out many what is it information or many diagnoses based on that. Okay, so some digital damage may be there, tissue might have broken. That you can see it in a computerized, not computerized, as they that digital radiograph. Okay. So there they are using imaging plate. So they just like that they will expose the imaging plate to the man, and then they will read it on your instrument. Okay, the instrument will be looking like a Xerox machine only. Just put the plate, the holder inside that one. Then you can read the image in the screen, computer screen, and then you can analyze it. Okay, diagnose the patient. If you go to CT scan, then that is a different type of technique, not like just 2D exercise. Tomography is very different. For example, you have a beam of some concrete beam, let us say, okay, if some porosity is there in the beam, okay, that you have to rotate the X-ray source and then record the image, and then you have to computeristically form the 3D picture of the same. And then you get the tomography. So tomography is different to the what is it called? Radiography.
So I think we can come to the conclusion. Many have started leaving. It's almost dinner time.
Yeah.
Yes. Yeah. So I would like to say a note of thanks to Dr. Sarnajirai. In fact, it's a very interesting session for me because we had the first-hand information from the one who is actually working on the X-ray diffraction. I felt like visiting IGCAR again. You know, It was really, actually, V.S. Sastry sir was recording all my samples when I did my PhD.
Did you analyze the
So
data?
maybe now you are.
No, but did you analyze the data? That is the most important.
Uh-uh.
Just you
Okay.
identify the face alone.
So it was really very nice, and in fact, um, and having you in this evening is really blessings for us, because we had lot of information. I know for students it is above their understanding level, but still, surely in later stage they will understand. Okay, these were all the things that was told to me earlier. Okay, so I like to thank Dr. Samadurai for all his efforts to bring a very complicated subject into a very simplified manner. You know, it's very difficult to understand X-ray diffraction, and that too to a lower level like us. It's really a very difficult task for you, and I know you would have put a lot of effort for this. So thank you very much for giving this experience for us. Okay, so tomorrow also we are expecting a lot from your side, and thank you all the participants also, because they are patiently listening. And I know it is difficult, but tomorrow we are expecting more interaction from the participant sides, and be prepared for the talk for tomorrow's session. It's going to be mind blowing, I know that, and be prepared and come back tomorrow.
Okay.
Thank you very much.
Thank you.
Yeah, thank you so
Thank you,
much.
sir. Thank you, ma'am.
Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you all. Participants are
Ma'am?
requested to be here at sharp 6 o'clock tomorrow. Thank you all.
Can I go in now?
Yeah, you can leave. So I think we have some audio problem.
Yes, ma'am.
Let's all unmute now and check whether the problem within our network or with the speaker's
No,
network.
now it's not. I think so, isn't it, ma'am? It's clear now.
Johnson, you talk.
Ma'am, am I audible at least now
Yeah,
properly?
you're audible now.
Yes, sir. You're audible now, sir.
Ma'am, I'll
Yeah.
tell you what the problem is.
Ah,
He was having his mic, and that was very sensitive, and that was picking the voice from his speaker. So when we talk,
I think we have to ask him to turn his either the mic or the speaker. I think.
it would be
Am I
better
right?
if he closes a external speaker and uses the headphone.
Headphone. Okay.
So that will restrict the audibility only to the ears, and that will not be heard out. So, for
Is
example,
he
if I have a
sharing
speaker,
from two different
external speaker
devices?
here,
Ah, it's picking up
Two
echo.
devices also he is using. That is
uh,
another reason.
That is the problem. He's
But
using,
one device is muting only, so it should not create problem.
but it will again echo. You cannot
The
use the
output
mobile
volume will
and
be
the
there.
laptop at the same time.
The
no,
speaker
the
volume.
speaker has to be put off there in the second instrument, not only the mic. So
Speaker
whatever
volume should be made 0.
should be minimized.
System which was he is using for presenting, and also we will ask him to use a headset.
Headset. I think he was
Headset
using a
actually is not
earplug.
necessary. He has to mute his laptop.
I
If
mean,
he
he
is
has to mute the
using the
speaker.
audio of the mobile, he has to mute his laptop. If he is using the audio of his laptop, he has to silent his mobile, mute his mobile. Every voice should be off. Either one device should be completely off. No audio, no receiving should also be off. It is not possible in the mobile to stop the receiving,
Exactly.
but it is possible to in laptop to stop its receiving.
Ma'am,
So
he has to put off the speaker in the laptop.
yes,
So
Sorry,
somebody
I'll try
can,
to convey to him.
yeah, he's,
So, were you able to understand anything?
but it was very simple. That he showed the diagram, not the diagram, the picture of an XRD. That and all was,
nice.
as he said, he simplified everything a lot. Somehow,
Actually, that was the instrument which I used in my PhD, the
Oh,
same lab.
fantastic, ma'am.
So,
I
nearly
was about to
thousands
ask
of
him
samples
whether
I have recorded in that.
their lab is, whether they are outsourcing.
I don't do that.
Ma'am, the meeting is still, still
Maybe you
it's
can
being
ask.
recorded.
Maybe you
Ma'am,
can ask. Ah,
the meeting is still
still
being recorded.
recording. Chansey.
Meeting is recorded. That we can trim.
Okay, we can cut it then. Okay, so I think today's program was. How do
Good.
you feel?